So here I'll give a quick example of axiomatizing structures. If we take the empty language, which is the language that has no predicates, no functions, no constants, but you still have equality, you still have conjunction and all the logical operations, so that's the empty language. So we can still construct a sentence phi n, which expresses n many existential quantifications, and then this long conjunction just stating that, you know, basically gaining every possible combination of distinct indices and stating that the two variables are not equal. So this is essentially a sentence expressing that n many distinct things exist, and then we take the class of all, or sorry, the theory, which is all such phi sub n, where n is any positive natural number, then this is an axiomatization for the class of structures with infinite domains. So that's one example. We can also axiomatize the classes, the class of linear orders. So these three sentences just express the basic properties of any linear ordering, and so this will axiomatize the class of all linear orders. If any structure has this less than, or sorry, any structure for this language with only the less than symbol will be a linear order, just in case it satisfies these sentences. So rather than go through all the, I've been skipping around examples in the book, not because they're not interesting, but just because I want to kind of, skip to the next interesting logic thing, so I'm going to do that here and skip over quite a lot of examples, and jump to the definition of logical consequence. We say that phi is a logical consequence of theory T if anything satisfying anything satisfying T must also satisfy phi. In that case, we write that T satisfies phi. But always remember that this is really shorthand notation for anything which satisfies T must also satisfy phi. So, easy to get these concepts mistaken, but the fundamental concept is that of a structure satisfying sentences, and from that we construct the notion of a set of sentences implying or having as a logical consequence some other sentence. Now, as a quick example, I'll take actually sentential logic, even though we haven't really been talking about sentential logic, but a structure satisfying this set of sentences in sentential logic intuitively would be something like one that has to satisfy A, and then also has to satisfy if A then B, but satisfying if A then B just means either not satisfying A or satisfying B. We've already assured ourselves that it does satisfy A, so it must satisfy B. Any structure satisfying this must, therefore, satisfy that. And I'll give more examples in the next video.